According to the National Electrical Code, specifically Section 250.122e, a grounding conductor is required to be installed in all electrical metallic tubing, otherwise known as EMT, conduits that contain electrical conductors. For this scenario of a 4-wire, 3-phase feeder, the minimum grounding conductor size must adhere to the standards set forth in the NEC. In this case, the minimum grounding conductor size is specified as number 4 American wire gauge, otherwise known as AWG copper. Moving on to the underground polyvinyl chloride, otherwise known as PVC conduit, NEC Section 300.5 it will mandates that a grounding conductor must also be installed in PVC conduits that are placed underground. Just as with the EMT conduit, the grounding requirements for a 4-wire, 3-phase feeder remain consistent. Therefore, the minimum grounding conductor size for the PVC conduit must also be number 4 AWG copper. In summary, the requirement dictates that a number 4 AWG copper grounding conductor must be installed in both the EMT and PVC conduits that are carrying the 600 ampere feeder. It's important to note that these are minimum requirements, and depending on specific factors, such as voltage drop or other considerations, it may be necessary to increase the size of the grounding conductor. Always consult the latest edition of the NEC and local electrical codes for the most accurate and up-to-date information. Also consider consulting with a qualified electrical engineer or licensed electrician to ensure compliance and safety. Grounding conductors provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protection devices such as circuit breakers or fuses. This is a critical safety measure designed to protect people and equipment from electrical shock and damage. The proper installation and sizing of grounding conductors are essential for maintaining a safe and reliable electrical system. When dealing with high amperage feeders, careful attention to detail is crucial. The selection of appropriate materials and installation methods must comply with all applicable codes and standards. Furthermore, regular inspections and maintenance are necessary to ensure the continued effectiveness of the grounding system over time. The NEC provides specific guidelines for the selection and installation of grounding conductors based on the size of the feeder conductors. These guidelines take into account the potential fault current levels and the need to minimize voltage drop during fault conditions. In addition to the size of the grounding conductor, the NEC also specifies requirements for the type of material, the method of installation, and the connections to ground electrodes. These requirements are designed to ensure that the grounding system is capable of safely carrying fault current and providing a low impedance path to ground. When installing grounding conductors in EMT and PVC conduits, it's important to follow proper installation practices to avoid damaging the conductors or the conduits. This includes using appropriate fittings and connectors, avoiding sharp bends or kinks in the conductors, and ensuring that the conductors are properly supported and protected from physical damage. In the case of underground PVC conduits, it's important to ensure that the conduits are buried at the proper depth and are protected from damage by rocks or other objects. It's also important to ensure that the conduits are properly sealed to prevent water from entering and corroding the conductors. When connecting grounding conductors to ground electrodes, it's important to use approved methods and materials to ensure a reliable and long-lasting connection. This includes using appropriate grounding clamps or connectors, cleaning the surfaces of the conductors and electrodes before making the connection, and protecting the connection from corrosion. Regular inspections of grounding connections are important to ensure that they remain tight and free from corrosion. Loose or corroded connections can increase the impedance of the grounding path and reduce its effectiveness in carrying fault current. In summary, the proper sizing, installation, and maintenance of grounding conductors are essential for ensuring the safety and reliability of electrical systems. Compliance with the NEC and other applicable codes and standards is crucial for protecting people and equipment from electrical hazards. Therefore, a number 4 AWG copper grounding conductor must be installed in both the EMT and PVC conduits. Always consult the latest edition of the NEC and local electrical codes for the most accurate and up-to-date information, and consider consulting with a qualified electrical engineer or licensed electrician to ensure compliance and safety. The grounding system is a critical safety component of any electrical installation. Its primary purpose is to provide a low impedance path for fault currents to return to the source, thereby facilitating the quick operation of overcurrent protection devices like circuit breakers and fuses. This rapid response is essential to prevent electrical shocks, fires, and equipment damage. A well-designed and properly installed grounding system minimizes the potential difference between conductive surfaces, reducing the risk of electric shock to individuals who might come into contact with them. Grounding also helps to stabilize voltage levels during normal operation and mitigate the effects of transient overvoltages caused by lightning or switching surges. The National Electrical Code outlines specific requirements for grounding systems, including the size and type of grounding conductors, the methods of installation, and the connection to grounding electrodes. These requirements are based on the principles of electrical safety and are designed to ensure that grounding systems perform their intended function effectively. The size of the grounding conductor is determined by the size of the feeder conductors it serves. The larger the feeder conductors, the larger the grounding conductor must be to handle the potential fault current. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the feeder conductors. In addition to the size of the grounding conductor, the material of the conductor is also important. Copper is the most common material used for grounding conductors because of its excellent conductivity and corrosion resistance. However, aluminum conductors are also permitted under certain conditions. The installation of grounding conductors must be done carefully to ensure that they are properly connected and protected. Grounding conductors should be run in a direct path to the grounding electrode and should be securely fastened to prevent them from becoming loose or damaged. Connections to grounding electrodes must be made using approved methods and materials. Grounding electrodes are conductive objects that are buried in the earth and used to establish a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the requirements for the number, size, and location of grounding electrodes. Regular inspections and maintenance of grounding systems are essential to ensure that they remain effective. Grounding connections should be checked periodically to ensure that they are tight and free from corrosion. Grounding electrodes should be inspected to ensure that they are still in good condition and that the connections to the grounding conductors are secure. Any damaged or corroded component should be replaced promptly. In this specific scenario, the 600 Ampere feeder requires a grounding conductor sized according to NEC Table 250.122. This table correlates the size of the ungrounded conductors to the minimum size of the grounding electrode conductor. For a 600 Ampere feeder, the ungrounded conductors are likely to be quite large, and as such, the corresponding grounding conductor size will be significant. The NEC mandates a number 4 AWG copper conductor or a number 2 AWG aluminum conductor. The choice between copper and aluminum depends on factors such as cost, availability, and the specific requirements of the installation. In this case, the number 4 AWG copper conductor is selected as the grounding conductor for both the EMT and PVC conduits. The installation of the grounding conductor within the EMT and PVC conduits must adhere to specific guidelines. Within the EMT conduit, the grounding conductor should be run alongside the feeder conductors, ensuring that it is protected from physical damage. The conductor should be securely fastened to the conduit using appropriate clamps or straps. For the underground PVC conduit, the grounding conductor should also be run alongside the feeder conductors. The conduit should be buried at the appropriate depth, as specified by the NEC and local codes to protect it from damage. The grounding conductor should be connected to a suitable grounding electrode system, such as a ground rod or a ground plate, to establish a reliable connection to earth. The connection should be made using approved methods and materials, ensuring a low impedance path for fault currents. Regular inspections and testing of the grounding system are essential to verify its effectiveness. Ground impedance testing can be performed to measure the resistance of the grounding path and ensure that it is within acceptable limits. Visual inspections should be conducted to check for any signs of damage or corrosion to the grounding conductors, connections, and electrodes. Any issues identified during inspections or testing should be addressed promptly to maintain the integrity of the grounding system. In addition to the NEC requirements, local electrical codes may impose additional or more stringent requirements for grounding systems. It is essential to consult with the local electrical inspector or qualified electrical engineer to ensure compliance with all applicable codes and regulations. The grounding system is a critical safety component of any electrical installation. Proper design, installation, and maintenance of the grounding system are essential to protect people and equipment from electrical hazards. By following the guidelines outlined in the NEC and local codes, and by conducting regular inspections and testing, it is possible to ensure that the grounding system performs its intended function effectively and reliably. Remember, electrical work can be dangerous, and it should only be performed by qualified and licensed professionals. If you are not familiar with electrical codes and practices, it is best to seek the assistance of a qualified electrician to ensure that the work is done safely and correctly. Ensuring a safe electrical installation involves many other considerations beyond just the grounding conductor size. These factors work in tandem to create a comprehensive safety strategy. Overcurrent protection, such as circuit breakers and fuses, are designed to interrupt the flow of electricity in the event of a fault or overload. The correct selection and coordination of these devices are crucial to prevent damage to equipment and minimize the risk of fire. Wiring methods, including the type and size of conductors, the type of conduit, and the methods of installation, must comply with the NEC and local codes. Proper wiring practices minimize the risk of shorts, grounds, and other electrical hazards. Ground fault circuit interrupters, otherwise known as GFCIs, are designed to protect people from electric shock by detecting small imbalances in current flow. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where the risk of electric shock is higher. Surge protection devices, otherwise known as SPD, are designed to protect electrical equipment from voltage surges caused by lightning or switching events. SPD divert excess voltage to ground, preventing damage to sensitive electronic components. Electrical bonding involves connecting all metallic parts of an electrical system together to create a low impedance path to ground. Bonding helps to equalize voltage potentials and reduce the risk of electric shock. Regular electrical inspections are essential to identify potential hazards and ensure that the electrical system is in good working order. Inspections should be performed by qualified and licensed electricians. Electrical safety training is important for anyone who works with or around electricity. Training should cover basic electrical safety principles, hazard recognition, and safe work practices. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and applying locks and tags to prevent it from being turned on. Personal protective equipment, such as gloves, eye protection, and arc flash suits, is used to protect workers from electrical hazards. The type of personal protective equipment required depends on the specific hazards present. Emergency procedures should be in place to handle electrical accidents, such as electric shock or fire. These procedures should include first aid instructions, contact information for emergency services, and evacuation plans. By implementing these additional safety measures, it is possible to create a safer electrical environment for everyone. Remember that electrical safety is a shared responsibility, and everyone should be aware of the potential hazards and take steps to prevent accidents.